So what I want to do is demonstrate how to run both a one-way and a factorial ANOVA in SPSS. The data set I have is a data set on salaries and departments and males and females. The argument that's being put forward by a group of employees is that males are being paid more, and that it is statistically significant. And the argument on the other side is that it's due to what department people are in and that different departments are being paid more. And so the ANOVA helps you kind of begin to sort some of that out. We can go over some of the interpretation online in discussion, but I want to make sure that you see this. So, assuming that you run descriptive statistics, you have a handle on all of that ahead of this. To run the ANOVA, you would go to Analyze, General Linear Model, Univariate. You can run a one-way ANOVA here, but it does not give you all the diagnostics that you need for my class. So use the General Linear Model, Univariate. This will give you this particular dialog box. And you need to think about what your dependent variables are and what your independent variables are. The independent variables are the fixed factors. In our case, we're looking at salary. We're looking at seeing whether salary is different between groups. And so that becomes our dependent variable. The two groups we're looking at, one is department and one is sex. We're going to run a one-way ANOVA right now, just looking at department. And this will give you a one-way ANOVA, and then we'll actually run the one-way ANOVA if you click OK. You need some more stuff to actually interpret this in a much more effective way. So we're going to get the plots here, and you're going to put department on the horizontal axis, click Add, include the error bars. You're going to get a post hoc test, which will allow you to see whether there are differences between, paired differences between different elements. You can go for LSD, you can go for Bonfiore, you can go for Tukey, you can go for any one of these. They'll all provide you roughly the same piece. Oftentimes I use Tukey myself or Bonfiore, so whatever works. They're interpreted roughly the same way. Click Continue. And then I want to go under Options. And even though you've run the descriptive statistics, it does create a nice descriptive statistics of means and standard deviations for you that's handy both for reporting and for reference. So I always run that. You want to run the estimates of effect size, and you want to know what the observed power is, or the probability that you're making a type 2 error. Click Continue. And now you can click OK. And then what you get is you get between subjects factor that says that you have 64 in human resources, 22 in marketing, 63 people in research. So those would be your ends for your different departments. You have the descriptive stats, the mean salaries, the standard deviations, and the total. So you can see how the different departments are paid different amounts, whether that's statistically different or not is part of the test. When you come down here with your, you get the test of between subject effects, multiple comparisons, and most importantly, you get an image. And to be honest with you, and we'll look at the differences, we'll look at this in a separate video. When you look at these differences, you begin to kind of say, oh, there really are differences between these and not between these. And so you can begin to hone that out. What I want to do right now is I want to complicate this with the factor to make this a factorial ANOVA. And again, you go to General Linear Model, Univariate, and we are going to add sex as one of the fixed factors. Now, for plots, you're going to add that to the line. You're going to add one more. So that you get through, you're going to get 3 graphs. Now, I'm going to do this and you're going to see an error. Part of the reason that you're going to get an error here is because there are only 2 options here. And so there's no need for a post hoc, and it will kick that out. If you have like a 3x3 ANOVA or a 3x4 ANOVA for your work, you're going to need that. So that's why I'm including it, but know that I'm going to get an error. And if you have a 2x3 or 2x2 ANOVA, you're going to get errors as well. All right. And then under options, I'm getting all those. All right. I'm going to click OK. I get my descriptive stats. I get my test here. I get the multiple comparisons, and I get the means. And you also get a sense about that men are paid more than women in all departments, and we'll look at the results more thoroughly as we go forward here. So let's go back and look at the results and actual pieces. You can look at the descriptives here for departments, and the marketing department seems to be paid the most. But if I lump all those 3 into the same group, are there real differences between those? And the place you're looking for is right here, where it says department. Oops. And your F is 7.3, P is less than 0.01. You reject the null that there is no difference between those two. Your partial eta squared is 0.09, which means that it's a rather strong effect, and your observed power is 0.93, and so there's really about a 6.4% chance you're making a type 2 error. So in essence, what you can really kind of make the argument is that different departments pay at different levels. P is less than 0.05, as you can tell down here. You're explaining about 10% of the salary, 9.2% of the salary here. If we look at comparisons paired-wise, all of these are significant except if you compare research and marketing. So one of the things you can say is that even though marketing is paid more than research, statistically it's not more. And so it could be due to random chance or random error. The other ones are statistically significant, less than 0.05, so there's a real difference, and it's unlikely that it's due to any kind of random chance. That will bear itself out here in this graph. When you begin to look at all 3 of these are declared to be different from each other as a group, but human resources is different than research, human resources is different than marketing, but marketing and research is not quite the difference. When you do a factorial ANOVA, it just simply compounds that. So we have a second main, so what we call this is this first one department here is we call this the first main effect. This is their second main effect. And this is your interaction effect. And so your first main effect is, is significant. P is F is 8.014. P is less than 0.01. You'd reject the null. That's actually the same one that you did with the one-way. For sex, F is 7.7, P is 0.006. You'd reject the null. Now, and those are 2 main effects, so you're looking at the actual main effect. But if you want to think about, do these 2 interact with one another, and is there an interaction effect when you put them in combination with each other? F is 0.727, P is 0.4. We'd fail to reject that. And so even though the department you're in seems to be having an effect on salary, and whether you're male or female has an effect whether you're on salary, those two are not working in combination. Those are actually independent things that are working in the system separately and apart. There's no interaction between them. And so that's an important finding. And this is the same multiple comparisons piece that you did before. The graphs are the same. This one's a little bit different, and this one really kind of indicates that you have some differences in sex in each one of these areas. So that's how to run and begin to think about interpreting your factorial ANOVAs. Again, you'll build those out based on the data that you've been assigned.